Hi, I'm Gareth Gvanison. You might remember me from such educational videos as Lead Paint, Delicious but Deadly, and Here Comes the Metric System. Today, we're going to discuss depolarizing pre-pulses, and in the process, answer the questions: what are they? Can we eat them? And why is this man talking to us? The vertebrate nervous system is divided into that of the central and the peripheral. The brain alone is estimated to contain over 100 billion neurons, many of which communicate with the sensory neurons of the peripheral nervous system. Neurons are excitable cells in the nervous system that participate in electrochemical signaling. This signaling can be achieved through the process of firing action potentials or transmitting graded potentials. For the purpose of this video, we will concentrate on the latter, where an action potential is a transient change in the neuronal transmembrane voltage generated by the activity of the neuron's voltage-gated ion channels. Typical action potentials are initiated by voltage-gated sodium channels. As the transmembrane voltage is increased, the probability that a given voltage-gated sodium channel is open is also increased, thus enabling an influx of sodium ions. Once the sodium inflow becomes greater than the potassium outflow, a potassium feedback loop of sodium entry is closed, and thus an action potential is fired. In the early 1950s, Doctors Hodgkin and Huxley performed experiments on the giant axon of the squid, and in the process developed a model for sodium channel conductance. It was found that the conductance may be expressed as the product of the maximum sodium conductance, m squared, and h, where m is the activation gate and h is the inactivation gate. The values of m and h vary between 0 and 1, depending upon the transmembrane potential. As the transmembrane potential rises, the value of m increases, thus increasing the probability that the activation gate will be open. And as the transmembrane potential drops, the value of h increases, along with the probability that the inactivation gate will be open. The rate of change for an h gate is much slower than that of an m gate. Therefore, if one precedes a subthreshold voltage stimulation with a hyperpolarizing pre-pulse, the value of h may be temporarily increased, enabling the neuron to fire an action potential. Vice versa, if one precedes a suprathreshold voltage stimulation with a depolarizing pre-pulse, the value of h may be temporarily reduced, enabling the inhibition of the neuron. The experimental results shown were collected from a space-clamped mammalian node of Ranvier. The model I've described is slightly inaccurate, as it fudges over some dependencies. For example, the inactivation gate should not be able to close unless the activation gate is open, and the inactivation gate, once closed, is located inside the cell membrane, where it cannot be directly affected by the transmembrane potential. However, this model is useful for gaining a high-level understanding of hyperpolarizing and depolarizing pre-pulses. One immediate application for depolarizing pre-pulses, explored by Drs. Paletto and Van Doren, is to elevate the pain thresholds associated with electrocutaneous stimulation. Electrocutaneous stimulation is a potentially useful communication tool for applications in virtual reality, sensory substitution, and sensory augmentation. However, many of these applications require the use of small electrode arrays, stimulation through which is often painful, thus limiting the practicality of this technology. The experimental setup was as follows. 4 human subjects were used, each of which had previously demonstrated the ability to provide reliable pain judgments. 1 mm diameter polished stainless steel disc electrodes were used to provide the electrocutaneous stimulation. A single stimulus consisted of a burst of 3 identical pre-pulse and stim-pulse pairs, presented at the beginning, middle, and end of a 1-second interval. The pre-pulse and stim-pulse widths were matched so that the thresholds would be the same for both. Paletto and Van Doren used varying pre-pulse amplitudes so as to study their influence over the pain experienced. Finally, the experiments were conducted such that the stimulus without a pre-pulse was painful for about half of the time. This was achieved by stepping the stim-pulse amplitude up and down for the next trial based upon whether it was reported as painful. The results demonstrated that a pre-pulse before a stimulus pulse effectively reduces the probability that pain will be experienced due to electrocutaneous stimulation. Surprisingly enough, a pre-pulse of 32% of the amplitude of the stimulus pulse was able to nearly half the probability of experiencing pain. Therefore, in environments in which the pain threshold is difficult to discern, it may be sufficient to deliver a relatively low amplitude pre-pulse before the stimulus to achieve the desired effects. So in conclusion, depolarizing pre-pulses are stimuli that precede the main stimulus and depolarize the neuron. No, you cannot eat depolarizing pre-pulses, and I still have no idea why I talk to you. Good night.